Hey, welcome to the final session on SystemVerilog Assertions. It's about properties. So we have already done two sessions. First session on the introduction part where we looked at what is a SystemVerilog assertion. Assertion is a way to concise and complete way of capturing waveforms, and how we can use that waveform representation for either checking, covering, or generating waveforms, or the generating stimulus through the formal tools using Assume. So we have looked at those aspects, and then we looked more deeper into the we looked at the three types of assertions. We have a simple immediate assertion, then we have a deferred immediate assertion, then we have a concurrent assertions, and then we looked at the layers of concurrent assertions. We have Boolean expressions. Using Boolean expressions, you can create timing expressions in the sequence, and then we looked at various sequence operators, and then we looked at how you can pass arguments to sequences, how you can use the local variables present within the sequences. We also looked briefly into the properties at the point when we looked into sequences. That part will repeat in this session, but in this session we will go more deeper into the properties part. We look into the different property types, and then the operators that are specific to property, and then we will look at how to put the properties in different units, and then like mainly the bind part. Okay, so there is a construct called bind. That's a useful construct. How to use that we will look at in the context of properties. So our overall agenda today is again three parts. So the first part will understand what's the scope of properties. Then we had looked at different, like 7 different types of properties. So we will look at each one of them, how to do negation, disjunction, conjunction, if else. Then we have already looked at implication, case. So we looked at type of properties, and then we'll look at some of the property operators, the if or the disable if operator. There's a popular use case, then followed by operator, next time operator, always, until, eventually. These give the validity to the timing expressions that we create using the sequences, which is the primary one of the primary tasks of the unique task that done by the property construct. And then we had looked at like weak versus strong. I mean, we had looked at one of the strong one example for the strong operator usage, and then we'll briefly look into the property recursion. Then so far we have looked at single clock examples, how you can use multiple clocks. We'll look at that. Then clock resolution, because the clock or the sampling event is one of the important part of the properties. Okay, and then there are various ways in it can be specified, and so how does it resolve when you use different ways. We will briefly look into it. And then directives, we have been using assert, and we have looked at some examples of cover as well. We'll look into a little bit more detail, and then we'll wrap it up by looking at the bind construct. So this is what we will cover in this session. Okay, so a part of it might be a bit of repetition, but what is the total scope? What does it mean to learn about the properties? Is that we need to understand these 4 aspects. We'll look at the property operators, and then we'll look at the property pattern, the 7 different type of properties. We'll look at that, and then multi-clock, clock resolution. We will look at these two, and then we will look at property directives. So if we cover these 4 areas, then we have completed learning about the properties. Okay, in the assertion, property is the final layer, and you can combine this layer with the directives to perform the intended requirement. And property declaration alone doesn't enable it. Like for example, just the class declaration alone doesn't do anything. The property declaration alone doesn't really take effect in simulation. It takes effect in simulation only when it is designated with one of the directives. You have to do assert, cover, or assume, then only the property takes effect. And then property layer is built on 2 other layers. The bottommost layer is your Boolean expressions, and then series of Boolean expressions are combined with the operators that we had seen in the sequence layer to define a timing expression which finally gets used in the property layer. And we have looked at it already, but formally property is the keyword. We give the name of the property. Then as we had seen in few examples already, in the case of while we are studying sequence, you can pass argument list to the properties on the same lines the way you can pass argument list to the task. You can pass the properties or the arguments to the property. You can pass the list of arguments, and then as we had seen, even in the sequence you can declare the local variables which you can use it at sampling at one particular sampling event, and then in the future sampling events the value that you had sampled in the previous sampling event can be utilized. And then you have the property spec. The property spec can be made up of directly the timing expressions that whatever we defined in the sequence, we can directly use it over here. Like for example, I can use a delay operator, repetition operator that I had studied in the context of sequence. I can directly use it in the property as well, or I can create more properties and I can combine them and make a new property over here. So that is the your property spec, and then it ends with the keyword end property, and this one has to be combined with these directives to enable it in the simulation. So property is a construct that captures the behavior of a system, and it can natively define the behavior using various operators that we have discussed. And for about the sequence, like for example, the delay operator can directly be used in the property, and also all the operators that we are going to discuss in the context of sequence can also be used in the context of property. And then the property has its own operators, and the primary function of those operators is to act like a precondition to filter out either inappropriate or extraneous situations that can happen in the sequence. So they provide some sort of validity to the sequence that we are using, and then how long a particular sequence needs to be active, or when is it going to become active. All that can be controlled using the operators provided by the property. And it's note that it's highly recommended that you build properties using the sequences because it makes understanding properties easier. But as we already have we are going to see that the properties are really tricky, and they're hard to understand. So if you build a very complex property in one place, then it's going to be very hard to understand. So if you break it up into smaller sequences and you give a meaningful name to the sequences, and then you compose a property using them, then it's much more easier for understanding, maintaining, and then debugging, and also the sequence can be reused. And as we have been emphasizing this point again and again, just declaring property doesn't affect any simulation behavior unless you combine that with one of the directive is when it really gets enabled in the simulation. That is your assert, cover, or assume. You need to add it to the property in order for the property to get enabled. And properties can be declared in module, interface, clocking block, program, package. I think they can be declared in any of these constructs that are provided by SystemVerilog. There are 7 different property types, or we can say property patterns. So this first one is a sequence in which you just use a sequence without any property operators, without any implication or anything. You just use the directly sequence within the property. That is your first pattern. Second is another property that you have built some set of properties. Either you build a new property using the properties that you have already defined, or you use a recursion. So that's called another property. Inverse is essentially either a negation or the inverting a property or a sequence that already exists. There is a disjunction. Disjunction is or of two property or the sequence expression. Conjunction, which is and of two property or the sequence expression. And then you have a if else, and here you use a Boolean expression to evaluate, and then based on the evaluation for true and false conditions, you'll have those two conditions, and for those two conditions you can evaluate either another property or a sequence expression in those blocks. So that is what you can do in the if else. and then you have a implication operator that we have already seen. This is a behavior, is a conditional behavior specification. The difference between if else and implication is that if else is based on a Boolean expression, whereas implication can use a sequence or a property expression as a condition. That's the main difference. Okay, here is a simple example how the negation property pattern works. So you have so you just write it as not of a property expression. So the example over here is I have a not, and this is the simple sequence timing expression that I am specifying A, and then after the assertion of A, 1 clock later the B must get asserted is the sequence, and I am negating it, and let's say how it behaves in the waveform. So we have added the assertion in the QuestaSim waveform, and then you have the clock, and then I have these values for A and B. A is asserted on this clock edge, it gets triggered, the property gets triggered that A is asserted, and on this clock edge it finds that the B is asserted 1 clock tick later, and hence the property has failed because this sequence is satisfied. As soon as it is satisfied, since we are negating it, this particular failure has taken place. Since both are asserted, the multiple threads get launched, and even on the subsequent clock edge also it will continue to fail. So this is how the negation of the this is how the negation pattern of the property works. So some of the property composition operators like the disjunction and conjunction, they help you to build more complex properties, but in the practical domain they do not have much of a real use. That's because when you build when you build properties by composing more properties, the overall process of debugging them becomes very hard. And even when you do the coverage analysis, if you don't know whether one of them has passed because of one of them has gotten covered because of whether it's a vacuous coverage or a non-vacuous, it's hard to figure it out. And when it fails, you need to now look into more closely as to which one has failed. So there are always better ways to solve this problem. You can keep them independent and assert them independent at a property level. At sequence level, you can probably OR it, but at property level, it generally is not doesn't have much of a use case. But the way it works anyway, for our understanding, we'll look into it. So the disjunction property is you have property expression 1 or property expression 2, and it succeeds when at least one or more of them are holding true. And if we compare the sequence OR versus the property OR, here you can see that in the first one, which is the OR of the properties, you are using a property operators, and then this is a real property. Okay, and here you have A implied, then you have a sequence X implied, whereas when you do the OR of sequences, this is an OR, this is just a Boolean expression, and then this is the implication, and then you have a OR of a sequence. Okay, so this is very different from when you do the property OR, because you are using the property operators inside each one of them. So don't think that the OR of property versus the OR of sequence, they are not exactly same. They are different. So let's look at the conjunction pattern. So the way it is defined is that you have property expression 1 and property expression 2, and it succeeds when both the property expressions either pass or match. Then here we are just comparing a sequence AND versus a property and of course they are not equivalent. They are not going to generate the same behavior. As you can see from this expression itself. Okay, so again the same point holds good, that overall when you use the AND of two properties, again it complicates your coverage analysis, because if the property has succeeded, then whether you don't know, like if one of them has passed vacuously and the other one has passed non-vacuously, and that's why you are seeing overall property as passing. And again, when it fails, you have to figure out which one has failed, and if it is combined, then it's hard to figure out. So like and especially you can just simply write it by writing them as two different properties, and either one of them fails, the overall property will fail. Okay, here we can look at the example of how we can use the if else. So we are saying if condition, then and then we are using a property, and then else we are using another property over here, and then so you can actually do the nesting, that is within if condition I can put another if, in the else I can put another if, and I can continue to do multiple levels of nesting. I think one point is, again, as we had looked at in the case of conjunction and disjunction as well, this one will complicate. If you do a lot of nested things, it will do the complications of coverage analysis as to what exactly led to the coverage. It will become hard to figure that out as to which branch really led to the coverage. So the more complex property by composition of using these type of constructs which combine multiple properties is generally is not recommended, and even if the assert fails, it's hard to debug. And if you have this type of a requirement, then you can just simplify it in this way, that you can say if condition, and you can say non-overlapping implication, then you can say T1, and then sorry, this is a overlapping implication, and then you say T1, and whatever your non-overlapping property that you had, you can continue. If condition, then you have another overlapping implication operator T1, and use another non-overlapping, or whatever the property that you had for the false, you can use that. You can use multiple implication operators, that is allowed. So you can simplify your if else with this type of a structure, and this will be much easier to debug if it fails, and for the coverage analysis also it is simple to analyze. So in the implication operator, the check on the property is performed conditionally on a match of a sequential antecedent. So we have already seen the sequence expression on the left side of your implication operator is called antecedent, and the one on the right side of your implication operator is called consequent. Right. So when the antecedent is completely matched, that is the endpoint of match of an antecedent sequence expression is actually the starting point for the evaluation of your property expression. Okay, so there are two types of implication operators. There's one which is called overlapping, and notice the way like you have a pipe minus and followed by greater than sign. So this is your overlapping. So here what happens is the endpoint match of antecedent expression is the start of consequent expression. It's the same clock. Okay, so for example, we had taken the let's say we have a request and we want to check, followed by that, like as soon as request is asserted, let's say we want to check the grant, right? We want to use the overlapping operator, and the same sampling event, as soon as the sequence expression is satisfied, you want the property expression to start matching, right? So the endpoint of your antecedent expression is the start of your consequent expression. That's what happens in the case of overlapping. And in case of non-overlapping, which is represented by pipe, and instead of minus sign, now we have equal to, and then you have a greater than. So this is the non-overlapping. And in the non-overlapping, what happens is you expect that after the endpoint match of your antecedent expression, the start of consequent expression start one clock later, right? That's what happens in case of non-overlapping. As the word is saying, non-overlapping, right? So on the clock event where your antecedent has matched, like I can say request, and then if I use an overlapping operator, it expects the grant to come one clock, next clock, right? Not on the same clock where the request has matched, but on the next clock. So that's what is the non-overlapping. And you can represent the non-overlapping using a overlapping implication operator. I mean, it's kind of equivalent. You can say #1, #1, tick true here being like the define that we had defined. It's like one tick P1 or tick 1, and then I can use an overlapping operator and say the property expression. And so this is the sequence expression double pound one tick true, that is one clock is passed, and then you can use the overlapping operator. So it's equivalent to this is the equivalent representation of non-overlapping using the overlapping operator, which makes it more clearer. So in the implication operator, right, on every successful match of your antecedent sequence expression, which is on your LHS, a separate thread is launched which tracks and evaluates the consequent property expression, which is your right hand side. Now, because of this, there can be multiple threads that can be active, and you need to keep this in mind because multi-threaded assertion can sometimes lead to a very confusing results. That is, an assertion could appear to pass and fail at the same clock cycles. That's because an previously launched thread could be seeing that a particular consequent matching its endpoint at a particular given clock edge, and it could be passing. At the same time, another thread could be seeing an violation and it could be failing. Okay, so this is very much possible, and this is something that we need to keep it in mind. And second thing is that with respect to multiple threads, it can so happen that multiple threads are launched when the your antecedent criteria is met, but same consequent matching can lead to termination of all of them, and sometimes you want it and sometimes you do not want it. Like for example, this request followed by an overlapping 1 to 3 grant, if the request appears 2 clock cycle back to back, then there are 2 threads that are getting launched. And what can happen is that eventually on, let's say, a second clock cycle grant comes in, then both the threads will get satisfied. So the thread wouldn't care that for which one the consequent expression is getting satisfied. As long as the consequent satisfies both the threads, then both of them will terminate. So this is something that you need to keep it in mind, that this condition can occur while when you use the implication operator, because you are guarding, still the results will be more less likely to face a false failure type of a conditions. But without implication operator, the threading can have a lot of side effects. There is another term that you will come across when you are using the especially the unbounded delay range. It's called vacuous pass. So what happens is when we take an implication property, let's take this is a non-overlapping. So we have a request followed by a non-overlapping implication operator, and it's saying $1 to $2 grant, that we are expecting the grant to show up by the end of current test simulation. Okay, and here the I'm just repeating, the antecedent is your request and consequent is grant. Now it can so happen that even when the end of simulation is reached, that the grant may never come. Okay, now since let's say the antecedent is met, that is a request has come but a grant never showed up, the property could still show that it is pass, and it's called as like a pass vacuously at the end of sim. Okay, the simulators could show this. Now vacuous means that emptied or lacking of content. It's a root in the word vacuum, right, in the air, what we call in the slang. Now there are two ways you can address this issue. So there is an operator provided called strong. So you can make the your consequent strong, so that you can say like request this non-overlapping implication operator, and you say strong of consequent, and then what will happen is that the simulator will not give you a vacuous pass on this type of properties. Or you can disable the vacuous pass using your assert vacuous pass as well. This vacuous pass actually affects when you are doing coverage, because it could appear that it is falsely covered. Okay, so if you are using it for coverage, then you want to take care that your coverage is not because of an vacuous pass where antecedent is satisfied but a consequent is not satisfied, and because of that you are seeing a property as pass, and that pass is leading to coverage bins being hit. So you don't want that to happen. So in such cases, you want to use strong and make sure that it is not showing a false coverage. But by default, this consequent has a weak type of a match requirement. We will see what is a strong versus weak in a bit more detail in future, but just keep this point in mind that when you have an unbounded range, that it can happen that a property might show as a pass but it has not really passed, and leading to false coverages. So here, this is how you can use the case type of a property pattern. It's a multi-way decision, and it's again based on a Boolean expression. This is something that you want to keep it in mind. And then, so what you can do is, once you have using a Boolean expression, you can use the values of it to branch it, and the search for a particular value is performed linearly, that is one after another it is performed. So here you have a case, delay, and if the depending on the different delay values, you are performing a different type of a sequence check over here. And default, you can say cause a failure if you can use it at the default value, that in case if the delay value happens to be X or Z, you can use checking for that. Again, we have already talked about it. If you write more complex properties, it generally also becomes hard to debug. So that aspect you have to keep it in mind. So you have this frequently the requirement that you want to disable the assertion evaluation under certain conditions, and it's very true that during the reset assertion you want to disable all your properties. It can be accomplished using this disable if construct. So here we are saying property after the sampling event, you say disable if and the Boolean expression, and then you are giving your property expression. And the point to note over here is that this disable if is not just evaluated at the start of your clocking event. Just because this clocking event has come before the disable if doesn't mean that it will only be evaluated on the passage of the clock, but it is evaluated all the time. That is, even if the property had started, let's say here if we had a timing expression, even if it had started and the reset got asserted, it will get evaluated. Or if the reset got asserted during the negage of a clock, it will still take effect. So at any point of time, think of it like an asynchronous, right? So any point of time the reset takes place, the property evaluation will be disabled. And a disabled evaluation of a property, it does not result in either success or failure. So your coverage sampling counts will not get affected, or you will not see any false failure, because it was either disabled before the start or got disabled during the execution of the property. So asynchronously you can disable any property evaluation using the disable if construct. Okay, we'll take a look at a followed by operator. So your followed by operator is in a way it's a dual of your implication operator. Implication operator is another property operator. It's a dual of that in some ways. It's a combination of, I think, the dual of implication operator plus the sequence concatenation operator. Okay, so let's look at how similar and how different it is. The usage is something as follows, the syntax. So you have a sequence expression, and this left hand side sequence expression is called as an antecedent, very similar to the way when we use the implication operator. And then you have the followed by operator. The followed by operator, similar to your implication operator, has this overlapping and non-overlapping variants. And then you can have a property expression over here. Okay, this is the main point. So your antecedent can be a sequence expression, but your consequent can be a property. Okay, in the implication we have generally seen that it is not a property, it is a sequence. Okay, but whereas when you look at the followed by operator, it's actually a property expression. Of course, there are differences. Just hold your thoughts over there. and the so when we see the examples, it will become more clear. But the bottom line is, all that it is trying to say is this property expression must be following this sequence expression either in overlapping or a non-overlapping form. That's all. So we have seen sequence concatenation, we have seen implication operators, so it's very similar to that. Okay, so a non-overlapping followed by operator is actually equivalent to not of your sequence expression with a non-overlapping, and again a negation of property expression. I know this whole thing, although I just wanted you guys to see the simplification form of it, it is not very evident by just looking at this particular expression. I think when we look at the example, let's jump into the example to gain more clarity. Okay, so here we have an example for using the followed by operator. So the requirement is that when we issue a USB command to, let's say, USB host controller, we want the host controller to start the DMA engine, and the DMA engine means that once the DMA request has been, the DMA engine has been acquired, we should be seeing a bus activity. That is, I have issued a USB command which requires a DMA engine, so it acquires a DMA engine, and then the DMA engine will start issuing the bus requests, right? Because it will do some sort of read write, it will transfer the content from system memory to your local memory, so it will start doing bus accesses on the bus that goes to your system memory. So these are the series of events that we want to assert. So let's understand how this property works. Now I am saying $rows of USB command. So now this is an antecedent for the implication, this non-overlapping implication operator, and followed by that now I have a sequence which is actually if this followed by operator would not have been there, then this would have just become a consequent for this implication operator. So now I have like a DMA request, within 1 to 3 I am getting a DMA ACK, and after this happens, okay, followed by that I want the bus access to be seen. Now this bus access that I am calling over here, which is actually a consequent for the followed by, and this timing expression is an antecedent for the followed by operator. And in this the bus access property that I have it over here, we have again an implication operator, because this is a property I can use an implication operator. So where I'm saying if there is a bus request within 1 to 7 clocks, I should be able to see a bus ACK that it has gotten it has gotten access to the actual bus. Okay, so in this one, the point to note over here is that at this point, that is in this middle of this property, okay, if this would have been a sequence, then we could have just used a delay operator and we could have said, okay, after this happens, then the particular sequence could happen. But here we want to use a property, that is, we want to build a timing expression that uses the operators of the property that are supported by property and not just the sequence. In that case, you can't just use a delay operator over here, because delay operator is a sequence operator. So you have to now use the followed by operator, which is a property operator, and combine that with the property. Okay, so the behavior is of the followed by operators for the overlapping is equivalent to your zero delay concatenation, and then for the non-overlapping it is double bound one, that is one after 1 clock delay. It's exactly same. Okay, so there the difference is that the only difference is that when we are combining with the delay operator, the right hand side of the delay operator, the one that comes on this side, is a sequence, whereas in case of followed by, this is a property. That's the main difference. So if I said this, like for example, sequence 1 and followed by operator strong S2, it is same as strong of, I can put this with the zero delay, and S2 is the same as this. Okay, now let's look at an example that whether if I put this in practice, does this behave the same way? Okay. So here I have four properties, and it's in general good to understand these basic properties, because so this the reason why I've done it to demonstrate this example of the followed by is also to showcase some basic things that we have discussed, but this is an important point that is worth repeatedly understanding. So here I have a property, and at passage of clock I have A and then a delay operator with one clock, and I'm saying B. So A, and in the immediate next clock it's expecting the B to get asserted, and then I am representing the followed by operator, the non-overlapping version, using the equivalent version, right? That is not of A, and then I have a non-overlapping implication not of B. I am using that, so I'm using that for to show you that it is equivalent. This part is equivalent as same as this. That's what we are trying to say. So let's see whether the behavior wise it matches. And then I am also putting an implication. This I am putting it just for the comparison. Okay, and I am adding one more where I am using the edge, the rows of A, and then if I change this implication with the antecedent that uses the edge detection, how the property behavior is different. So in this example I am not just showing you how the followed by operator works, but also these basic expressions, how their behavior becomes different. I would like you guys to pay attention and understand. So if we look at this, the top one, A simple, so this is the assertion for that property. If you see on any clock, if the A is not asserted, it is failing, and on this particular clock edge now the A has been asserted, and on the next clock edge, so on this clock edge it gets detected, and on the same clock edge we have asserted the B, and on this sampling event the B gets detected. So now it sees that one clock delay difference, and as soon as A has been asserted, our property has gotten activated, and on this clock edge property is satisfied. Okay, and on this clock edge onwards the property is failing because we do not have the B assertion. Okay, we have the assertion of A, but we do not have the assertion of B. If we had kept the B asserted throughout, then this property would have passed. So the point to note is, when you don't have any implication operator, it would expect the A to be asserted on all the clock cycles. Okay, that's what is expecting, and since it's expecting A to be asserted one clock delayed, it was expecting B to be true on all the clock cycles, and whenever that is not happening, it will lead to failure. Okay, so that's what is happening with the A followed by one delay operator B. Now if we see this followed with the delay operator, now if we see the same thing with the followed by equivalent, the behavior is exactly similar. So wherever this A delay with the 1 is failing, the same points, the same sampling events, even the followed by is failing, thereby showing that this is really equivalent to this. Okay, the non-overlapping followed by is equivalent to your just the sequence concatenation. The only difference is now it's doing the property concatenation. So you can think of it like that. Okay, and then whenever there is the implication one we have seen. So if you see the implication one, it has not failed here. Okay, because if the antecedent is not satisfied, it's not going to check for the consequent, and if antecedent is not satisfied, then it is fine. It's not a property failure. Okay, so you are not seeing a failure, whereas when I had put just A, the delay operator of B, it was expecting A to be true on all the clock cycles, but whereas when I use implication, it's not expecting that. Now, but subsequently on the, when it sees the assertion of A and then it sees the assertion of B, it has passed, but on the subsequent clock cycles it has failed because it's not seeing the B, and antecedent is satisfied, but since the consequent is not satisfied, this assertion is failing. Okay, that's why even with implication we are seeing the failure. Now if we see the rows over here, it's not failing at all. Okay, that is because it is only sensitive to the edge. Okay, so it sees the edge only at this point. So the pre-poned region over here would have sampled 0, the pre-poned region here would have sampled 1, and since it has sampled 1, that's the edge detection. 0 followed by 1, that's the definition of the rows function as we had seen in the sample functions in case of sequences. So the property has gotten activated, and then it was expecting 1 clock later the B to be found. But now, even though A stays 1, it doesn't bother this property, because there is no more transition that is seen on A, that is the dollar rows of A is not satisfied. So there is no problem. Okay, so I want you guys to like contrast between them and understand this fundamental difference very clearly, because this is a very important point. It not only clarifies followed by, but clarifies these various possibilities and how do they behave differently. So between these two, I wanted you to see like how does a level sensitive versus the edge sensitive behavior of the property changes. Okay, let's look at the next time property operator. So the syntax for the usage is you say next time, and then you say a constant value that can be derived using a constant expression, and then you have a property expression, and this is essentially equivalent to our delay operator that we have seen it in the sequence context. So I could be saying double pound a constant expression for a sequence expression, okay, and the next time constant expression is for the properties. That's the only difference. Okay, so I could be saying next time of some constant, and then if I say property expression, it's actually similar to, I am really putting double pound C here is like either 4, 5, whatever, some n constant n delay, then one tick B1 to make it that it is true, to make the property progress further or the sequence progress further, and then we are using an overlapping followed by operator with the property expression, so is equivalent to that. It's just that you can now say that compared to the point where the sampling starts, that you want it to be delayed by some number of sampling events, and thereafter the property expression to evaluate true. Okay, so some of the sequence operators you cannot apply to the property, that's why there are some equivalent ones. But the point to note over here is that when you build these property operators generally help you build more complex properties, and in general a complex property is not a good idea, so you want to keep them as simple as possible. So you should try to again break it up into a simpler sequences and then use them over there, rather than using the property operators and then building more complex properties. So you have to just think about it in on those lines. Okay, let's understand the always operator present in the property. The point to note is that for any of the concurrent assertions, there is always an implicit always present. Okay, with all the concurrent properties that we have seen so far, there is always an implicit always that is present, because they are always active, right? A concurrent means that it is always active at all the points, and it gets evaluated on every clock tick or the sampling event that we have specified in the property. It will always get evaluated on that. And this always operator is mainly used, like it has a more usage in the formal verification word for there's a concept called liveliness and safety properties in formal verification. So that's where these operators get used. In the simulation world also they have few use cases, but they are mainly meant for these use cases. You can actually search for them. When you get a grasp on the basics, you search for this and you will be able to find some examples as to how the liveliness and the safety properties are used in the formal verification. So for now, let's look at one example of how where the always could be used in the simulation world. Okay, so here we have one requirement that we want to make sure that the reset is asserted for only 5 clock cycles, and after 5 clock cycles, after first 5 clock cycles, the reset should be deasserted and should remain deasserted throughout, right? That's what we exactly want. That is our requirement, and if that is our requirement, we can implement it this way. So we are saying property at passage of clock clock, we are saying it's an active low reset, so it should be asserted, which means it should be low for 5 consecutive clock cycles. And we have an non-overlapping followed by operator, and we are saying thereon always a reset must be asserted. Now this whole functionality I can represent it with this equivalent code. I am just using the equivalent code to make it easy to understand these operators. So what I am doing over here is, first I am just creating one assertion wherein I can put the concurrent assertions within the initial blocks as well. So I am putting one concurrent assertions which says that it asserts that for the first 5 clock cycles the reset is asserted, right? That the reset is 0. So this is done by this property p asserted first 5. And while this operates concurrently, now I need to wait for those 5 clock cycles. So I'm saying repeat 5 at pause edge of clock, and then in a forever loop on every pause edge of the clock I am doing an immediate property check saying that reset is true. Okay, and this forever with always with a passage of clock, whatever this that I have put it over here is equivalent to your like always passage of clock as well. Okay, and this entire thing is essentially your always reset, and so that gets replaced with this part of the code. And if we look at the behavior of these two properties, so I have put this property and this property. So this property, you can see that it holds true for the first 5 clock cycles. If the reset is asserted, this property is happy. And then here I have created a case where the reset goes low. Okay, so during this region, this particular property is not active, so it's not doing anything. But after the first 5 clock cycles have been completed, then we are seeing the reset is deasserted. If I assert back the reset, then this property will fail. So that is how the always block will behave. Okay, let's understand the until property. So the usage is something as follows. So you have property expression 1 until property expression 2, and the second usage is property expression 1 until with property expression 2. The first one is non-overlapping use, and second one is a overlapping use case. So as the name suggests, you want the property 1 to be true just till at least 1 clock before the property expression 2, because you want them to be non-overlapping. So there should be 1 clock gap between these two, and within the property expression until with property expression 2, there should be 1 clock overlap between these two properties. That is what is this particular operator is expressing. And if we look at the equivalent forms, it will become more clear. So here I am saying property expression 1, the unbounded repetition, and then I am saying delay operator of 1, then property expression 2. So this unbounded happens, and then you have 1 clock delay, and then only this has completed, and then you have the property expression 2 starting off. And then property expression until with, which is a overlapping, we are using again an unbounded property expression 1, but here we are using the 0 delay concatenation, and hence there will be 1 clock overlap between the property expression 1 and property expression 2. Let's take a look at an example. So what we are saying over here is that requirement is that the request must be asserted until ACK goes high, and then request must go low. That's our requirement, and this is our property. So we are saying $rows of request, and we are using a non-overlapping, the overlapping implication operator, and we are saying request until with ACK, and then followed by that 1 clock delay, and the request must go low. Anyway, this part is an additional part that we have added. Our primary focus is on this one. So if we look at the waveforms, the request has gone high, and as soon as the request has gone high, the antecedent is satisfied, and hence the our assertion has become active, and then we are seeing that ACK has gone high, and both the request as well as ACK, they have 1 clock overlap. They are saying request must stay high until the acknowledgement is asserted, and they must have one clock overlap, okay, till the acknowledgement is asserted, and that is happening. And there on one clock next sampling edge, the request is the request is also going low, and the acknowledgement is also going low. Of course, the acknowledgement going low is not checked, so the request is going low, and that part is checked with this particular expression, Boolean expression over here, and hence at that point the property ends. We'll look at the property operator eventually. The usage is something like this. You say eventually a constant range followed by a property expression. This actually equivalent to your delay range operator. Okay, so the delay range operator, we were using it for the sequences, whereas the eventually is something that you can use it for the properties. That is the only difference, and it just allows a better expression for the in the formal verification for doing this safety and liveness check. What is safety and liveness check is something that you can search for it in the context of formal verification and understand it further. We will not be covering as a part of this course. So the next operator is we have this operator called strong. There have been three versions of LRM that have been released so far. One is 2005 of SystemVerilog LRM, 2009, and then we have one in 2012 where it became an IEEE standard. In the 2009 LRM onwards, if you wrote a property using an implication operator, then it was considered as by default a weak property. What does that mean is that if at all a request came in, and then if I have an unbound range, then if the consequent doesn't show up, that is in this case the grant doesn't show up, still the property will pass, okay, because it is a weak. Whenever you especially have the unbound range, so it will pass. But if you put a strong, and then what happens is if the request gets asserted but the grant doesn't show up by the end of test, then this particular property will fail. So that is the effect a strong operator has to make the unbounded range non-weak. That is, if they are not satisfied, it's going to show up as the failure at the end of the test. So that is the use case. Now there are going to be cases wherein you want the property to remain weak, okay, that if that doesn't happen, probably it is good that it didn't happen, okay. So you don't want it to fail, but you want it to fail if it happens. So some cases could be there, so in those you can use a weak. But if you think that it is mandatorily required, for example in the request followed by grant, probably it is required, so you have to. And if you are using unbounded range, the unbounded range you should not, you should use it carefully, but if you are using it, then you can use the strong over there. And even the other operators that we saw, like next time, always, until, eventually, until, with, they all have a strong flavor associated with them. So if your context is, they are by default weak, so if you want to use them in the strong context, you can use S prefixed version of the same operator, and then that will behave as a strong. That is, if there is unbound range, then it will lead to failure, okay. So that is the usage of the strong operator. Okay, so the recursion is possible with properties, and there are two types of recursions possible. One is that a property is self-instancing itself. That's a classic version that we would have seen even in the context of procedural programming. And then there's a mutual recursion where, like, a property A calling B, B calling A, and they have a cyclic dependency between them. And what happens in the procedural context when you do the recursion, you are calling a particular subroutine again and again, and then there is a particular condition that gets satisfied, that you check in the recursive subroutine, and when that condition is satisfied, you return from that particular subroutine, and then the values are pushed on the stack, and based on those values you compute something and return back from that particular subroutine. So that's how the procedural recursion works. Whereas when you look at the recursion in the context of properties, there is no return. Okay, there is no real return. It simply specifies that a thread of evaluation should begin executing whatever the named property that you are starting off. There is no stack associated with the property recursion, and there is infinite property recursion possible because the previous threads would either be satisfied or failing. So you can continue doing infinite recursion because you are not storing anything in the stack. But as we know, even in the procedural programming, your recursion is not a everyday programming pattern. It is generally considered as hard to maintain and debug, and there are additional restrictions on the usage of recursion in the property. But we will look at one simple example, practical use case where we can use recursion. Okay, let's look at an example of a recursive property. So what we are going to do is, let's say if I have written this always p. Okay, what this would mean is that on whatever the sampling event that I'm using, on all of the sampling events, the value of p must hold. That's what this always p would mean. And if I were to write an equivalent version of it using recursion, then it would look something like this. So I have property my always, which is my version of the implementation for always, and you can pass the property itself as an argument to a property. Okay, that's possible. So you can pass a property, and then here I am saying next time of 0p, which means on this particular clock cycle, and next time I am calling the same property instance again. So I am calling this property instance again. I am calling my always of p, and then this will keep it will keep on going this way infinitely. Okay, and this will equivalently translate to next time of 0, and then next time of 1, and next time of 2, and so on and so forth. Okay, and so this recursion will not end. It will continue infinitely for many ticks, as many as they come in. And now the question will come in your mind that okay, we already have an always. So what's the real use case for this type of an implementation? There is one use case for this type of recursion based implementation that typically what we have seen is the SVA constructs, right? They always support a finite constant range of something. Okay, so but if you want to use like a variable range, like for example, if you wanted to implement always low comma high, low colon high, and then the low and the high you wanted to use variables here instead of constants, then you can use this recursion method and implement my always property with these additional arguments, and then you can create a construct where it was only supporting a very static constant range to something that is variable range, and for that you can use the recursion. So this is one use case for recursion that you can apply. However, as we discussed, recursion is an advanced topic. Okay, so far in all our examples, we have been using a single clock, like at passage of clock or at clock, something like that, right? So we have never used multiple clocks. Both the sequence and properties can be constructed using multiple clocks, or they can be constructed by using different edges of clock at different points in your sequence. So it's possible, and if you but this comes with certain limitations. As we saw, even the recursion comes with some limitations. So any very flexible constructs of the properties, they do come with some limitations or the restrictions, and they will have their own nuances as well when you push them to the limits. So if you have a differently clocked sequences, then they can only be combined using the sequence operator, this hash 1 or hash 0, and then hash 1 will mean when you are combining with a multi-clocked sequence is the nearest subsequent tick of the second clock where the sequence begins, and the double hash 0 will be the nearest overlapping tick of the second clock, and if nearest overlapping tick is not available, it will become nearest subsequent tick in the real usage. What that means is I cannot do at pause edge of clock 1 some sequence 1 intersect sequence operator with at pause edge of clock 2 of S2. This is not possible, so I cannot use it in this way, and I cannot even do at pause edge of clock 1 S1 with a 2 clock delay, and I will say at pause edge of clock 2 of S2, the sequence 2. So I can only use the double pound 1 or double pound 0. Only these two operations I can use to combine the different sequences which are using different clocks. Okay, but yeah, so this is one limitation that you have to live with. Okay, let's take a look at one practical example of how we can use multiple clocks. So many of the designs actually use multiple clock edges, like for example DDR, right? So they use both the pause edge and neg edge to transfer the data, and if I were to implement some checks on such interface, what I can do is I can say property P1 at neg edge of clock fell A, which acts as antecedent. It's clocked at neg edge of clock, and then I have an overlapping implication operator, and then I'm saying at pause edge of clock fell of B. So I'm using two different edges. From the properties point of view, it's a different sampling event. So between two different sampling events or two different clocks, it's no distinction. So here it will catch the nearest pause edge after the this occurrence of a neg edge. So you can implement DDR type of a checks using the multi-clock sequence. So you can multi-clock sequence or property. This one is a property, so you can use multiple clocks and then you do the DDR checks. We have already looked at multiple usages of assert directive. Just formally we'll define it. So assert statement is used to enforce a property, and on true evaluation the pass statement action blocks gets executed, and if the property fails, it's the fail action box that gets executed. And if we don't specify, so this is optional part, the pass action block is optional, whereas fail, if you don't specify, then by default it executes a $error statement which will display the property failure in your log file. And then cover directive, there are two types of cover statements that you can actually utilize. You can actually cover a sequence itself, or you can cover a property. Assert is always on property, but cover you can do on both of them. And then tools collect the coverage and report the results at the end of simulation. So you can say cover sequence when you say it will track all the matches for each evaluation attempt. So if it matches on every evaluation attempt that is used by any number of properties, the sequence coverage count will keep incrementing irrespective of whether the corresponding property completes or not. But the cover property, then coverage property count gets implemented only once per evaluation attempt of the property. So that's a difference between your sequence versus the cover property. Okay, when you use the cover directives on property in your coverage report, it will report how many times it was attempted, how many times it succeeded, and how many times it is succeeded because of the like a vacuous pass for a property. So it will report these. And when you attempt cover on a sequence, it will report the number of times attempted and number of times matched, because each attempt can have multiple matches for a particular sequence, so both of them will get reported. And when you write the cover directive where you say cover property and name of your coverage, the property that you have written on the pass, you can, like, pass means whenever it is hit, you can put some block of statements over here, and those will get executed, and they can sometime help you do the debug, or some additional information that will be helpful for you to count and sometimes match with what has been reported. So if there is some confusion, it will help you resolve those. So we have seen how implication operator helped us prevent many of the false failures. But when you use a property in the context of coverage, the implication is not always your friend because of the obvious passes. There can be sometime the false positive in your functional coverage unless you are paying attention to all the numbers, right? That you're actually looking at whether the pass is showing due to OQS or the real coverage hit. Sometimes you may not realize it in the high level summary. So to prevent it, if you are writing a property for only coverage, then instead of implication, you can consider replacing implication with a concatenation or a cycle delay operator, so that when it really happens is when you are seeing and there's no OKS or the false positives showing up. So assume is another directive, and assume allows the property that it is combined with to be used as an assumption, meaning that the tool has to work to satisfy it rather than checking, which is your assert case, or covering, which is a cover, where the design behavior is resulting in observed values, right? So there the design is doing some work and you're either checking it or covering it, whereas assume is something that you're telling the tool has to do the work. So in the formal, it can guide the generation of input stimulus to the DUT to create various cases and to prove that the asserts that we have are all holding up. So and then or discover a pattern where it is not holding up and it is failing. But in simulation, the assume doesn't have much of a role, but you can use it to check the assert the values of the variables that are generated by the test bench itself, because test bench also should generate a legal stimulus. So sometimes you can use assume to check, but yeah, it doesn't have much real value in the simulation, but in formal it is very useful. So we have expect directive. So expect statement can appear anywhere you use your built-in wait statement. It's equivalent to that. The expect statement causes whatever the process that is calling the expect statement to wait for the property to succeed or fail, both, either of them. It will wait for wait for it to succeed or fail. Like for example, we are showing an example over here. So we have a task automatic wait for, and we are passing a few arguments, and then we are saying expect, then we are writing the property over here, property sequence itself, we are directly writing expect at pause edge of clock, and then we are delaying it by some 1 to 10 clock cycle, data is equal to value, then we are passing success equal to 1 or success equal to 0, and then we are saying wait for this particular value. Okay, so we can do that, and then whenever the property succeeds or fails, it's going to come out, and then we can use the check the value of this variable to figure out if it has succeeded or failed. And then the expect gets scheduled to execute right after processing the observed region, where the property completes its evaluation. So after this, the expect gets scheduled to execute. So you can use that. You can use the properties that have been defined to cause the wait. But one challenge with using the concurrent assertions in this form, like for example, assume or expect in the test bench, is that test bench is a class based word and you cannot use them in the class based word. Okay, concurrent assertions, as you have seen, they can only be instanced either in a module or an interface or a clocking block or a program block or a checker, which are all static entities. You cannot instance them in the dynamic. Only the immediate assertions can be used in the dynamic word. So although expect might look very attractive, but you cannot directly use it in the class based test bench verification. Okay, so the you know that in the properties, the sampling event or the clock is a very important part of it, and the resolution means which one gets used can be figured out using this small chart that we have created over here. The resolution comes into play because there are multiple ways in which a clocking event for a property can be defined, and when if multiple things are defined, then how do you figure out which one gets used? That's where the resolution comes into play. So one is that you can define a default clocking event, which can be like at a global level. Wherever it is not defined, then the default clocking event can be defined, or you can define properties within the clocking block. So let's say now you have defined properties within a clocking block, and then there's also a default clock, then the clock in the clocking block would get used. Or there can be a possibility that you have used a default clocking block, but there is a way that contextually inferred clocks, like for example, if I have an always block, I'm using certain clock, then the properties used within that always block can contextually figure out that I need to use the always blocks clock. Okay, so if that is a case, then that will override the default clock. Okay, and then I might have a contextually inferred clock, and then I might have the default clock definition as well. But if I have defined a clock within the property, and then the property clock will override these two. And then if I have defined a clock within this actually should be a sequence clock. So if I have defined a clock within the sequence, then that will override the clock defined at property level, and that will override so that will override all three. So I might have a default clock, I might have a contextually inferred clock, I might have a property clock, and if I have a sequence clock, that will override all three of them. So basically the lowest level definition will generally override the upper definition. We are not talking about multi clocks. They have some more additional rules that makes this whole resolution slightly more tricky. We are not going to look at it over here in this session, but you can refer to LRM to understand that further. Okay, so we have the way you declare some of these is that you can say default clocking and master clock. Okay, if you say this, then any property where the clock is not defined, for example, here I have a property P2A delayed by 2B end property, and when I say assert property P4, the A and B will be sampled using the master clock. Okay, both the edges of the master clock, they will be used over here. And then I might declare properties within the clocking block, and the event that I have defined for the clocking block will be used as a sampling event for this particular property. And then if I use properties within the always block, then contextually it will infer the clock used over here as a sampling for the A and B of this particular property. Or I can have we have already seen this, right? Like we can define the clock within the property, and then that gets directly used. And the sequences, generally we have seen inheriting the clocks from the property, and but you can explicitly define a clocking event or a sampling event within the sequence, and then whenever you have that, it will override if there is any clocking defined for a particular property. Okay, so in this case, now what will happen is the default clocking is master clock, but here since the sequence is using the this particular clock, then whatever the passage of clock, so it will override the master clock, and it will use this passage of the clock. So that's how the resolution function works. Okay, so let's say you have a scenario where you are implementing some assertions based on microarchitecture as a part of your verification effort. Then what happens is it's a sort of white box check that you are implementing, and you are using certain signals provided by your design, but you don't want to include your code in the design code, because design code ownership is not with you, right? The design code ownership is with the design team, and sometimes in some of the organizations it might so happen that there could be different repositories, and the design might get released to the verification team. The original code of the design is somewhere else, and the copy of it is released through another branch for the verification team. So you can't really go and change the design code. So in such scenarios, how do you write your assertions? So one of the construct that has been provided in SystemVerilog is called bind, and what the bind allows you is that it allows you to instance one of these following either a module, interface, program, or a checker in a target code without really having to do it within that code. Okay, so and any auxiliary code that you require for assertion or white box coverage can all be placed into the target module by creating an instance in a non-intrusive manner, that you don't have to like really, let's say I have another module, test module, where I have written some assertions. Now in order for these assertions to become active, I will have to instance this particular module in that particular target DUT where all the signals are located, or I have to like use hierarchical path references to keep passing them, which is non-portable. Instead of that, I can use a bind, and I can say bind my test module to this particular target path, and then it will automatically create an instance of this module inside that, and then it can then behave as if it's present over there without being like physically present. So it provides you an ability to instance one of these constructs from somewhere else to in somewhere else in your design code, okay, without physically having to change the code. So and that helps you improve the reusability, because verification related checks stay in the verification part of the code. I think like once we look at an example, it will become more clear. So bind itself can be specified in either a module, interface, or your compilation unit scope. It can be specified anywhere, and bind can be done in three ways. You can either bind it to module, and then it automatically get instanced into all instances of that particular module. Okay, so that's one way. Or you can bind it to a specific module instance name. Okay, then again for this you have two options. You can do it without hierarchy. Then if you do it without hierarchy, then all instance name at different hierarchy will be bound. Okay, so you can use, because different hierarchy forms a different namespace, so you can use the same module name at different module instance name at a different hierarchy. So if you bind it without hierarchy, then it will get bound to all of those instance names, and if you do it with hierarchy, then only that specific instance name in that specific hierarchy will be bound. So these are the three different ways in which you can do the bind. Now let's look at an example. So here we have a checker module. Okay, it's a checker cum coverage module. So I have written a property over here in this checker coverage module that I want it to be bound, and I have a DUT, so I have a module DUT, and the ports of this DUT I'm using them in my property that I'm using it for I can use that for coverage or check, it doesn't matter, that's not the point. So the point is that I have a checker and coverage module, and I have a property, and in that property I'm using certain signals, and I want these signals to be the signals of this particular DUT. So at the test bench top, I would have created multiple instances of this DUT, let's say, and then what I want is I want to bind it by the name of the module. Then the way bind works is I will say bind and then to which module I'm going to say to DUT port. So in this case it's going to be bound to both the port 0 as well as port 1, and then I am going to say which module needs to be bound. So I'm going to say DUT port checker and coverage, that is this particular module name that needs to be bound, and then I can give one instance name I'm giving over here, and then I am going to say for these signal I am connecting by position, the signals of this particular DUT. So I am passing them. Once I do this, then it's as if that I have taken this particular module and instanced it over here. Like let's say at line 247, I am, let's say, instancing this particular module with a DP1 and connecting it to these ports. It's same as that when I do a bind, but whereas I'm doing this bind at the test bench top level and not inside the DUT port. So this way I can insert an additional verification code into design without really having to change the design. So this is how the concept of bind works, and it is very helpful. It is very helpful even for like creating some of, you want to create any, the bind concept is not tied to assertion. Okay, in this module I can put any code. So like let's say if I want to print something, debug information from DUT, some statement FSM that I want to print, or I want to do any additional behavioral check, not just the property based check, I can do anything over here using the bind. But typically bind is used in the context of assertion, so we have covered it over here. But bind is a generic construct, and it can be used to insert any verification code into your design without really having to go change the design code. Okay, so this concludes the session on SystemVerilog properties. So, and this also concludes that we have looked at the like what does it mean when we say we want to learn assertion. We have looked at it, and we have looked at like three types of assertions: the simple immediate, and then deferred immediate, and then concurrent assertions. And we looked at that concurrent assertions are made up of layers. There is a Boolean expression layer, there's a sequence layer, and then there's a property layer, and that property layer is combined with the directives, and the directives are placed in a unit like a compilation unit, or we use interface, or we use modules, checkers, program blocks, we can place it in over there. And then each of the sequence has its own sequence operator, so we have looked at those. And then how we can make sequences more reusable by passing parameters to them, and then how we can use the concept of local variables within the sequence. So we have looked at that, and then we have looked at properties, then the 7 different property patterns. And while we covered them, we looked at many like we gave some guidelines as well, that we should not construct too complex properties using the property operators just because they are available, because the debugging them becomes very difficult. So we have looked at that, and then we completed those 7 different patterns, and then we looked at the property operators. Then we looked at how the strong versus weak type of operator affects the property evaluation. We have looked at that, and then we have looked at how the clocking resolution works, that if I have specified clocking operator, the clocking event in different places, then how if multiple places, and how it gets resolved. We have looked at it. And then we have looked at the bind, which is a construct that is very useful in being able to instance module in another module, and how that module can be used to keep your assertions or any test bench related code. I know the assertion is one of the long and the tough construct of SystemVerilog, and as we have talked about, it will take minimum 2 passes so to really understand. So in one pass you should really look at each construct and do some of the simple examples on them, and provide different stimuluses, and develop the thought process that we had talked about, that when does it start, when does it end, and what are the different pass under different conditions where it is going to pass, what are the different conditions where it is going to fail, and then are there any hidden type of scenarios, mainly due to the threading concept that we discussed. Do those come in, that we have to look at it, and then apply it for some of the simple projects, and look at it. But at the same time, assertion being a tough area, it's useful in both the dynamic simulation. About 15 to 20% of the overall checks in the dynamic simulation at interface level are implemented using the assertions. It is growing in the simulation world as well, the usage, but in the formal verification it is much more useful. So yeah, so you have to practice more, and then so once you are able to use it in some real project, the third is learning about more and more advanced things, the restrictions, the nuances. Of course we have not covered everything, okay, so you have to still refer LRM. So this gives you the lay of land for assertions, but this doesn't mean each and every aspect of it is like, especially we have covered all the operators, but each operators have certain restrictions and then certain nuances. So those aspects we have not covered as a part of this session. That will become too long, and it will not be interesting also, because some of it, when you encounter some problem and when you look at it, you understand that better. Without that, if we keep on telling, it becomes very, I mean, it is not engaging, and as well as you will not be able to appreciate it. So those are some things. As you practice, you have to keep it in mind that you are going to have some restrictions and limitations that are going to come up, and as and when they come up, you have to look more deeper into the LRM, or look at the different forums to understand why it is so and find out the solutions for that. Okay, so thank you for listening.